There's two types of lighting that I wanted to discuss in this lesson. First one, which we see right now on the screen, is called a ambient light. And there's a couple of things to understand and know about the ambient light. It's basically the light that is coming from many directions. There is no specific directionality of light. The ambient light would come from almost like a dome of color that is being projected on your 3D space. So for instance, if you have your 3D space like right here, you are going to have a dome around it like this. And this dome will pretty much from every direction, it will project a light. So every single point on that dome will project a ray of light. And this ray of light is basically going to go across this construction that we see here, for instance. And what's going to happen is, because there is no specific directionality of light, what you're going to achieve is something that is called ambient shadows or ambient occlusion. And basically what it means is that the shadows are going to be very soft, and they're going to appear only or mostly in places where the objects that you see right here are closest to each other. So for instance, when we look at this red sphere and it's sitting on the ground, you can see that this red sphere is where it's touching the ground, it's creating the most of a shadow, and the shadow is very soft, very diffused. Much like those columns, as close as you get to a bottom of that box right here, you can see the columns are getting darker and darker, and especially also right here, right where the capital is, you can clearly see that it's those areas are much darker. Those two boxes that sit on top of those 6 columns, you can see they are not connected perfectly, and the distance between here and here, right, is so small that this line or this space in between is going to be really dark, because the ray themselves are not able to reach that area so much anymore. When you think about ambient occlusion, you have to think about how light rays are working and how basically light is working. So when you have a surface, and let's draw like a little surface right here, and you have a ray of light that is hitting the surface, what's going to happen is the ray of light is going to reflect in one direction. Now, this is ideal situation for very glossy, almost very specular surfaces, which mean one of the best examples could be a mirror. So every single ray that goes and reaches the mirror is going to reflect directly and going to create perfectly sharp reflection. When you, however, get to be working with a diffuse material, this reflection is going to scatter, which means it will be broken down into spinnes. The ray of light is going to reflect. Light rays are working and how basically light is working. So when you have a surface, and let's draw like a little surface right here, and you have a ray of light that is hitting the surface, what's going to happen is the ray of light is going to reflect in one direction. Now, this is ideal situation for very glossy, almost very specular surfaces, which mean one of the best examples could be a mirror. So every single ray that goes and reaches the mirror is going to reflect directly and going to create perfectly sharp reflection. When you, however, get to be working with a diffuse material, this reflection is going to scatter, which means it will be broken down into smaller rays that have less power, and basically the result is very blurred reflections. And the same way it works when you have a surface and the light is hitting it. So maybe let's draw on this side, and let's make a surface like this. So the light rays that are hitting here, you can see that there's quite a few that can squeeze between, right? But then that's pretty much it. And those light rays will start losing energy as they bounce around. remember that all the lights are basically bouncing around. So you can see that those rays will eventually start there's going to be a diminishing return, or the light power or the bounce of the light, the energy of the light will start start to be smaller and smaller, and eventually it will disappear. So there's no light, let's say right here, there's really little light coming in here. So what you're gonna have is this gradient that, this area right here where you have all the light rays hitting the surface directly. Let's say they will have 100% brightness, but as soon as the light bounces in this area, the brightness will be, let's say, 80%, and in this area it's going to be 60%, and right here it's going to only be 40% because there is no direct light hitting here anymore, and then in here it's going to be 20%, and so on and so forth, eventually reaching 0%, where there's not enough energy coming from the light to create enough light information so that you can actually see color and surface property. It's just going to be really dark here, and this is exactly what's happening here. This space in between is very narrow, which means not that many light rays can reach it, and eventually just becoming really dark really quickly. Whereas here in the open space, there's enough rays to hit those surfaces to give you still those very soft gradients without going too dark. And that's exactly what is happening. That's exactly what is happening under the ball. So the bounce, the amount of light that is bouncing right here is very little, right? Where the amount of light that is bouncing right here is much more, and here is just like purely there's a lot of rays and a lot of rays. Again, think about all of those rays coming from different directions, which means one will come from this direction, the other one will come from this direction, one from here, and one from from behind your chair, one from the depth of the image. So in this area here, you're gonna have light rays that are coming mostly from this direction and maybe from the sides, but those rays that are coming from the center of the image or from the depth of the image will be occluded by this structure right here and those columns and the sphere itself. And thus, when you look at the surface itself, you can see that it's slightly discolored and just darker, basically. And that's pretty much how ambient light works. When you think about ambient light in video games, it's going to be related to global illumination, which basically ambient occlusion, and it will just create those really soft shadows around spaces. In most cases in video games, it's going to be light that is baked in, which means it's painted in the texture. However, on some of the PC games and the next generation games that are coming out, and obviously the technology is changing constantly, it's becoming more and more real time. So you actually can have ambient occlusion and global illumination happening real time in some of the game engines as we speak. In consoles, for most of the console games, those effects of this really soft lights, because they are so heavy to be calculated, in most cases they will be done as light map. It's called a light map or vertex map. And light map is basically a texture in which you're gonna have brightness or darkness painted in, and that would be basically what the shadows, those soft shadows, gonna look like. Vertex map will mean that there is a gradient, so from very dark to bright, and this coloration, this change of coloration, will come from vertices that are on the corners of a polygon. And basically, if you break down this, let's say you break down this column, this column in video game, the way it would build in 3D would be basically, you know, a net of polygons that are connected to each other. And if you would want to have that little gradient right here, and you would want to use vertex map, you would have to have like a really small space in between. So let's say this is our rectangle, and this is the gradient that we're getting here. And the vertex map would mean that this edge right here is black, and this edge right here is, say, dark gray. And then the gradient between those two edges would create this this sort of ambient occlusion illusion, or ambient light or ambient shadow illusion that we see right here. This is obviously 3D render, which means the ambient occlusion and the shadows are going to be much more accurate than they would look like in the video game, because obviously the render itself, when it's done via CPU, when it's done by a render engine for a 3D application, is much more accurate. This render was actually done with Corona, which is an unbiased render engine, which basically means that it will try to calculate shadows and light as accurate and physically accurate as possible. So this is interesting and very important information to understand, because there are a couple of types of light that will basically use light maps and vertex maps, and basically will be the ambient light. And one of them is, you know, very obvious skylight, or you know, the light is coming from the sky color. That's super obvious, because when you have something that is in the shadow, there's no direct light, it will still be lit by any other light sources, and your sky, your blue sky itself, for instance, is a source of light. The bounce light, which we've discussed so far, is also a source of light. So even if something is in shadow, the light is bouncing from the surface and going opposite direction is going to cast light. So this is a great example right here. The bounce light and discoloration of light, depending on what kind of surface it's hitting, it's called, and we've mentioned this, a global illumination. And it basically means that the ray of shadow that is going right here, it's reflecting down. If it's going right here, it's reflecting down here. And then from here, it can go and reflect back. So this is a great example. Here, you see that little outline in between the shadow itself and the sphere. It's because we have a ray of light that is hitting the ground and bouncing back on the ball. And it's just lighting the ball right here, and it's making that little color that we see right here. So those are the things that are going to be important to know. Actually, this ray itself would bounce back and make this area a little brighter, otherwise it would be just very dark. And this is basically how it works. You know, the light is bouncing always. It's always going to reflect from surfaces. If the surface is reflective, it's going to reflect as a mirror, or maybe, you know, you're going to have some reflections. If the surface is diffuse, it will have no reflections and whatnot. But general idea here is to remember that ambient light will mean very soft shadows, and that's pretty much it's sort of like to distill it to one sentence. Ambient light means soft shadows. The next light we're going to talk about is a direct light, and direct light is basically the most common light that is used in video games, and it's basically what it is and basically what it sounds. It's a light ray that is strong, and it's coming from one specific direction. So right now we have our sunlight that is coming from a very specific direction, and it's casting a very obvious shadow that is coming from the structure itself. So we've discussed about, you know, constructing shadows. This is obviously 3D render, which means the shadows are going to be extremely accurate. We don't have to make any constructions. 3D render is basically doing it for ourselves. But this light is very different from the ambient light. One thing you have to, however, remember is both direct light and ambient light are going to be mixed together, and this is exactly the situation. never in the real life or in your paintings, especially when you work on a painting, you should never consider only one specific light. So for instance, if you make a decision that you want to have a direct light, you should also make a decision you will have an ambient light. Ambient light is always going to be there. So that's really important to remember, because light, the property of light is that it's always reflecting, it's always bouncing from the surfaces, which means the bounce light or the global illumination, which is a term to be used in 3D rendering and also in video games, means that the bounce light will happen, and the bounce light itself is also considered to be the ambient light. So there's nothing much more that needs to be said. Usually, actually almost always, direct light is going to be real time, and it's almost in all game engines. And real time means that this light will affect every single object in real time. If your character is moving, you'll see that the shadow of the character is reacting to the way this character is moving. If the character gets closer to say a wall, the shadow of the character is going to be cast on the wall and whatnot. It's not the light that is being baked specifically into surfaces like we've discussed would happen with light maps and vertex maps. It means it's just real time. It's just happening as it goes. It's calculated on the go, and the shadows are being cast on the go. And it's in most video games of a present, you will have one singular real-time light, and sometimes you'll have more, but that depends on game engines. Some game engines can handle more than one direct light, but it's also a lot of it's consuming a lot of resources from whether it's a computer or the PC computer or Mac, or if we're talking console game development, which is almost the majority of video games right now, it will actually take a lot of resources. So you have to be really careful how many direct lights you can afford. And in most cases, for most video games done for consoles, it's just one direct light per scene. So that's something important to remember. In terms of painting and using this knowledge to paint, think about direct light being, let's say, it could be a sunlight that is being, that has a specific directionality. It could be a lamp that's, having a specific directionality, and maybe a cone. Sunlight will be probably have more parallel rays that will just go in one direction and create very uniform shadows, whereas artificial source of light would stretch the shadows depending on the light position. So all those things matter in painting, but one important thing is that we will have that ambient light still in this render. So when you look at this render, you can see, okay, we have sharp shadows that come from the direct light. So anytime you see sharp shadows or shadow directionality, you know that there is a direct light in the scene. But we also have those reminiscence of ambient occlusion and global illumination, which is looking, everywhere that we see shadow, it looks very similar to our previous scene. So when we look back at our previous scene, you can see that all those shadows that we see here are exactly here still. The color or intensity will look different. You can see that the reflections, because this is a glossy material, which means it's reflecting, are different depending on the light. Right here, it's the light is pretty much very bright, or a bright white light is affecting the whole scene. Here you can see that the light itself, it's more blue, which means we have a blue dome for a skylight that is affecting those surfaces. And that's pretty much it. That's pretty straightforward. The shadow, the color of the shadow will actually come from the ambient light. The directionality come from the direct light, and that's pretty much what you need to know at this point to make a distinction between which light is which and how to use it. The next topic I wanted to talk about is sharpness coming from scale of the light source, and also shadow edge softening with distance. And that's basically connected directly to the scale of light. So let's look at those examples right here and discuss exactly what is going on and why we have a different sharpness of the shadow, and why we have this shadow here being really soft, whereas this line right here is more sharper, obviously, and with the distance is going to be slightly blurred. And the reason for it is really simple. Let's look at let's draw a little quick lines here to explain exactly the idea behind it. So when you look at this shadow right here, and the reason for it to be really sharp is that we have almost a point light, which is right here. The light source is really small, which means the amount of rays that will overlap, so the rays that are coming from this light are basically coming from one point, which are like this. Whereas in this situation that we see here, you're gonna have a ray that is going like this. But also each point, imagine that each of those points from which the ray is coming, it's also casting another ray that is going in a different direction. Which means some of those will overlap and create more or less light. And that's exactly what is happening here with the shadow. So it means that you have maybe one or two rays hitting here, but the further away you go, the more rays are hitting those surfaces right here, and eventually there's so many that it's indistinguishable. You cannot see any shadow. So let's draw it maybe from the side, where we have a little box right here. So we're gonna have a ray that is coming from the furthest angle of that whole sphere, and it's just being cast like this to the ground. But also we're gonna have a ray that is coming from right here that is being cast to the ground. Let's just assume maybe there's like a lid right here. So this area right here is going to be very dark, but there's more and more rays coming here and here. So you can see that the further away from this wall we get, the more rays are going to eventually hit. And here there's no occluding object, so all the rays can hit right here, and it's just gonna get really dense and really dense. And basically, so right here we're gonna have 0% of light, and then maybe this is going to be 25%, and here it's going to be 75% and 100%, right? So you see that the distance between 0 and 100% is quite large. Whereas if we draw it right here, I know it's a little bit funny to look at, but this is just to show you the idea when we're sketching it. So because let's assume this is a point light, this is a very small light right here, so it's only going to be a ray that is coming from that one point, which means there is no overlapping of the rays. And so we're gonna have 0% and almost 100% right away. So the distance here, this is going to be dark, and then all of a sudden it gets bright. So that's exactly what is happening here. You get from 0% to 100% almost in an instant, which creates this very sharp edge. And the situation right here is the closer you get to the edge of the object, or where the rays are starting to hit, and the further away you get, the more rays can cover that ground. Because right here in this very small areas, there's going to be a limited amount of rays that can hit that ground. Whereas if you go further in that direction, there's more and more points of where the rays can hit, and eventually creating that 100% situation. So this is exactly what is happening. So we get from 0, 25, 50, 100%, right? This is the coloration change from dark to bright. And that's briefly about how shadow softness works. What you need to remember is that the larger the light source, the softer the shadow is going to be. That's pretty much sort of distilling down to the most possible simple rule about this subject matter. And when we look at the shadow softening with the distance, this is exactly the same situation. The distance between so when we look at this situation right here, which is we have an overview, and this block is exactly what it is here. So the distance between, say, this point and where the shadow casting is happening is just right here, or maybe this point and here, right, is very small. But you can see that there's an angle, and it's going to be probably at this point, or maybe a further point like outside of the canvas, which is casting this shadow, and it's going right here. So this is exactly the meaning of how the shadow is softening. In this situation, we have a light source that is slightly larger. It's maybe between this point light and this huge sphere. I would assume is maybe like a smaller light, like this size. And this size of a light would have a little bit of sharpness where there is small distance in between the surface itself, or the object that is casting the shadow, and the ground. But the further you go, you will see that the light is becoming softer and softer. And if there's an object on the way, that object will have a soft shadow cast on top of it. But this object itself will almost restart the way the shadow behaves. So again, in this situation right here, you can clearly see that the shadow starts from sharp to soft again, and it's exactly the same situation. So when you look at point A and when you look at point B, those are the same situations. It's basically there's a new object, and the new object is casting a new shadow, but this object is sitting in the shadow, half sitting in the shadow of object B. That's why you see that soft shadow right here. A great example of this situation would be lamplight. So what you could do a test, put a lamp on the desk, and put few objects on the desk and see how shadows behaves, and maybe put the big object that is casting the shadow on the smaller object that is maybe half in the light and half in the shadow, and see how blurred the shadow on the object itself is going to be, and how sharp the shadow of this smaller object that is there on the desk, how sharp it's going to be. So and that's going to give you a little better idea exactly how it's looking in real life. But basically, in those renders that you see right here, this is basically how the light is going to behave depending on the scale, and this is how shadow will change and become softer and softer with the distance. Why am I talking about this? This is really important because shadows and what we're going to discuss next, which is global illumination and reflectivity, and specular versus diffuse reflections. All those things will matter for you to create surfaces and images that look realistic or look fake. Knowing how shadow and light behaves in real life and how physically it works will allow you to make better choices and better decisions where the shadow should be sharper or where the shadow should be maybe softer. This is important because your eyes are already accustomed to that knowledge, because you see it from the very moment you're born. You start to see light, you start to learn light and colors, and after a couple of months you can understand how lights work. Your brain starts to register it and engrave it in your memory. And when you see something that looks fake, you'll clearly see something that it's not really looking good. because you're born with understanding of light. You understand the light. You see it every day, and if something just is not following the natural way the light works, it's never going to look realistic. So having that knowledge will help you to create more realism in your images, and will actually help you to create more compelling concepts. Let's talk about specular versus diffuse reflection. We have 3 different spheres here, and then each of the sphere has a different glossiness setting. And the first sphere, the red one, is on the 100% glossiness. The second one is at 50% glossiness, and then the third one is at 10% glossiness. Now, glossiness itself is a setting that allows you to change how blurred reflections are going to be. So at 100%, which depending on what kind of render engine you use, whether it's percentage, it could be a texture map that you add that has a different black and white and grayscale values. But basically what it means is whether it's 0% or 100%, or if it's black and then it's a gradient through grays to white, where white would be 100%, it means that the ray that is coming towards that sphere is only going to reflect once as one singular ray. At 50%, what you could imagine what would happen is that this singular ray that we have here that is reaching the sphere would actually reflect in many more ways, and at 10% it will be just a lot of those small rays reflecting in all the directions. Now the reason why you have those blurry reflections is also because you get that second ray, and then those rays, those different kind of reflections are basically intersecting to each other, and each pixel that you see is an average of, if we just draw like those little boxes that represent pixel, for instance, is an average of different rays and how they reflect. So if this is 100% of a ray, and then this is 100% of its reflection, this would be 100%, and all of those would be, I don't know, maybe 10%, and each of those would be like, you would have 10% or 20%, and you would have 5 rays coming out. This is just an assumption number, just to give you a perspective. So this pixel itself would have a couple of rays that are 20% opaque, and because you merge them together, you blend them together, it creates this this reflection that you see here that is very blurred compared to what you see here. This is a perfectly sharp reflection on the sphere. And much like with 50%, 10% would have even more rays that intersect and blend to each other. So for instance, here, the reflections are perfect. Here, the reflections are probably an approximation of this kind of little box. In here, it would be an approximation and blur that is coming from this amount of rays. So glossiness, basically, just to explain it as easy as possible, will define how much reflection you see. And this is important because all of the materials you see in real life, whether it's a material that can clearly reflect, like mirror or maybe a glass or water, those materials have different glossiness, but all of them reflect. Even your pair of jeans does reflect light, but in very small amount and in a very small glossiness. So that's really important to remember, because reflectivity and reflections and specular versus glossiness, those things will determine how realistic your material is going to look like. Which means if you paint a brick, or if you paint a plant, or if you paint a structure that is painted, the paint itself might have reflectivity. in it. So for instance, oil paint will reflect depending on what angle you look at. That's called Fresnel. That's something we'll talk about in a second. But basically, reflections are extremely important. One of the most important and integral part of how lighting works, because what you see, the objects that you see in space, our spheres that we have right here and here and here, you only see them because light is reflecting through them or out of them. If light would not reflect on those surfaces would be pitch black. But because there is the reflection, you can now see them in your space, on your canvas. So that's an extremely important thing to remember and understand, that reflections are everywhere. Now it all comes down to the angle of reflections and how much glossiness the material has and all those things. But long story short, glossiness, the percentage of it would determine how sharp your reflections are. And then obviously there's another aspect to reflections, which is the intensity of the reflection. That could be determined in scale from 0 to 100%, or from 0 to 1, or maybe in the gray scale. And also it could be determined by a color value that would basically the color or the wavelength of the color that is reflecting would tell you exactly what color this material properties are having. Okay, so we've discussed specularity versus glossiness and how glossiness affects the way the material looks like. Now let's talk about the index of reflection, or in short, Fresnel effect. Fresnel effect is basically telling us what amount of reflection you're going to see based off the idea how the camera is positioned towards that object. So right now what we see is something that slightly resembles perfectly still water. And the way I've created this, I've created just a box material in 3D, or a box object in 3D. I placed my camera and my HDRI map, which is basically that map that is casting all the lights that we need to have in the scene. And what we have here is something that crudely represents, a water or perfectly still water in the desert. And you can see that it's almost perfectly reflecting everything. The angle at which the camera is looking at compared to where this water surface is, if we would just draw this surface right here, and the camera would be sitting very close to it. So this would be our camera, and the angle of view towards that water would be probably around 10 degrees. Okay, so once we establish that, let's look at what happens if we move that camera a little up. So we're shifting this camera that we have right here, and we're gonna make it so that it's more of a 30-degree angle, and we're gonna place our little camera right here. So let's look what happens to the reflection itself. And what you can start to see is it's still reflecting a little bit of that clouds, a little bit of environment that is around this surface, but it starts to show what's underneath the water surface, right? Obviously, this is not perfectly how the ground would look underwater, because we're not taking into consideration how the light is bending inside the water and how the depth of this feels, and also the material beneath is just the dry sand, so obviously it doesn't look correctly. But pay attention to this area right here. You can see that there is a reflections, but the material becomes somewhat transparent. It feels washed out, and it feels like there's some reflection going on because the sky itself is mostly clear. It has that little haze of a reflection going on. But now let's enable the camera that is looking straight down. So if you look at the image right here, this would be our camera, and would have a perfectly 90-degree angle. And let's see what exactly happens at that situation. And now you see that there's almost no resemblance of the water surface whatsoever, the water material whatsoever. It's just none. It doesn't exist anymore. This material becomes perfectly transparent. And this is how your Fresnel effect will work like. So when we enable back our surface right here, at this angle, our reflections are going to be anywhere between, say, 90 to 100%, okay? At this angle, our reflection will be down to, say, 30%. And at 90-degree angle, our reflection's going to be 0%. There is an index of reflection. It's called IOR. So in short, index of reflection. And for water, that index is somewhere roughly around 1.33. It's a value, it's a mathematical value that you input in a 3D software. And once you input that value, the reflections will act like they would act on the water. And this is exactly what I did. And this is exactly the results you see right here. So this is really important because when you think about Fresnel effect and when you think about reflections of the water, for instance, depending on what camera angle you're going to look at when you paint your image. Let's say you're drawing your image and you're making a surface of a lake, but you want to have water that looks natural and looks real. Obviously, this is 100% reflective because the waves and because there are waves, basically. So the surface is not perfectly flat. Right now here, the surface is perfectly flat, which means the reflection is going to be perfect. But if the surface is not perfectly flat, it's more wavy like this, then your reflections will have different angles depending on where they land, right? And this will create the result of wavy, blurred out look and whatnot. So depending on how frequent the waves are, whether it's a calm lake or a stormy water, the reflection is going to be more or less glossy because those rays that we see right here that are traveling and hitting the water surface, if it's a calm water, it's going to look like this. It's going to be wavy. But if it's a stormy water, you're not only going to have more random looking surface, but also there's going to be air particles or water particles or evaporating water in the air that will scatter the reflection even more, which will make this look much more glossy. And in most cases, when you have a light source and there's a water, what happens is you often see that there's this kind of effect where the light sort of depreciates and becomes more and more blurry and wavy, and it's just looking like that, especially like a moonlight and the surface. And this is exactly because of the glossiness of reflections. But important part here to remember and understand is the fact that when you look at even this image, you can see that here in this area on the bottom, on the 30% of the bottom right here, right? You can clearly see that we have a little bit of translucency or a little bit of transparency going on here. And you can see that surface beneath the water right here very mildly, but you can still see it. Whereas right here, where it's really far away, you don't see any of that. So when we go back to this diagram, and let's maybe draw it right here in the middle, so we can see a little better. And we have our camera right here, really close to the water. You have to remember that the ray that goes out and looks at here, this is probably, let's say, 1 to 5%, right? Or 1 to 5 degree. But when it's closer to the camera and the camera still sort of has this cone of view that is more or less like this, right here at the very bottom of the image, this angle is going to be more like 10 degree, perhaps, maybe more. Okay, so that's important because the smaller the angle, the more of the reflection you're gonna have. So this is pretty much what you need to know about how Fresnel works. It's really important because every single object, every single material in every single material in real world has a Fresnel properties, has the index of reflection. Now that index is going to be different depending on what material you're using. So for instance, if water has 1.33, chrome might have something around 3.8, which will mean it will be much more reflective on every single angle you look at. So this is really important to know and understand and get into, because once you understand how Fresnel works, every time you paint something and every time you construct something in 3D or in perspective, so let's say we draw our box here, right? And this is our, this is our horizon line. We're constructing our box right here, and and we're making it like this. We'll know that the camera is looking at this object, and it's probably around, I don't know, maybe 45 degree right here, maybe 60 degree, just eyeballing the degree. And now we know, okay, if this material is based off a plastic or metal, it will have a Fresnel, and it will probably reflect some of the light. Then let's say this is a sunlight right here. It's a really low sunlight. You will have a little bit of that reflection going on right here, especially like right where the light is. So it will just diffuse right here, and it's not going to be so present on the bottom, but it will be just like almost in the straight line. So this is a really important lesson to take, because this is what is going to make your materials look more or less realistic. So I'm right now just kind of sketching how the reflection would look like if it was really glossy, or if this reflection would be really specular. It would be almost a full representation of that sun reflecting right here. Now obviously you would have to construct and see exactly where the sun would be positioned, or if it would have even the same shape. Probably would be more squeezed like that, but still it would reflect. And then depending on how diffuse this would be, you would have this blurriness going on. So this is why IOR, index of reflection, or Fresnel is really important, because this is how your reflection is going to work on all of your surfaces, and this is how your surfaces will reflect ambient light or direct light or any other light sources that you have in the scene. Finally, let's talk about global illumination. And what exactly is global illumination? Because I've mentioned this before, and I just want to give you a better explanation how exactly global illumination works and what it's going to mean for your paintings. So we have this little scene right here. There is a direct light coming from the sun, and we have this very simple setup of diffuse materials, diffuse boxes that are basically creating this sort of small scene, this little corner of two walls and the little box that is sitting against those walls. Basic idea behind global illumination is that the light itself is bouncing, and the bounce light is bouncing on the surfaces, and depending on the color of the surface that the light is bouncing off, it will affect the nearby surfaces as well. So this is pretty simple to understand when you look at the red wall and how it's affecting this wall right here. You can see that the red reflection that is coming from this wall, when we have our light that is hitting right here, it's reflecting back and then reflecting on this wall right here. And you can see that because this area right here, this little triangle, is actually darker, it's the reflection of itself, and how global illumination is going to reflect on this white box will actually represent that here as well. So because of the darkness of this wall, you can see that it's darker right here, and the brighter the reflection, the more visible the coloration of the surrounded area is going to be. You also have to remember that the surface, the darker the surface, the less affected it will be by that global illumination. And it's pretty obvious when you look at it here. For instance, this surface right here is pretty dark, or it's darker than this white surface, and thus it's not having a lot of that red influence in it. However, you can see that there is slight influence of that red color in the shadow. Global illumination will be very almost invisible or slightly visible or almost indistinguishable if it's directly in the direct light. So for instance, in this area right here, we will not see all of that global illumination, if at all. We maybe see a little bit of it, but not too much of it. So but when you look, for instance, at this surface, you can see how green it is, and because this wall eventually ends, it starts to discolor from green to more of a bluish, and the bluish is coming from the basically the light, the ambient light of the sky. So you can see that coloration here. And of course, in this corner, when you look really closely, you can see that this shade that we have here, the hue, is different than this hue. This hue is more tinted towards red, and this one is tinted towards green. Now let's enable a grayscale just for a second, and you can see that the white box itself is actually causing a little bit of that global illumination as well. Look at this corner right here, how dark it is, or even just this area here. It's pretty dark, but when it gets closer to that box, you can see that towards those edges, especially in this area right here, it's getting a little bit of that brightness. Not too much, but still just slightly so. I mean, the percentage, if this is, say, 65% of gray, this would be maybe 62% of gray. So even the box itself is affecting global illumination. Something to pay attention to, because it's going to be pretty important. Global illumination, basically, that's pretty much it. That's how it works. How are you going to use it in your paintings? Well, pretty simple. When you have surfaces that are close to each other, you'll remember that if you have a corner and there's like a red wall, you'll have a little bit of that red coloration in the red wall. If we're only talking about values, for instance, when you have that white wall, really white wall, you'll have a little bit of that reflectivity going on here. Even though this is not a reflective material at all, it has actually zero reflective influences. I'm only doing it for a purpose of showing you how global illumination works, and we're using specifically diffuse materials that have no reflections. If those materials would have a little bit of reflection, you will actually see more of a mix between global illumination and reflection itself. So I only wanted to show you the global illumination, and you see that this white box is causing a little bit of that reflection here, or actually it's basically lightening this material right here. So likewise, if you have a dark material, it's actually not going to affect any of those edges or any of those surfaces, but the brighter the material, the more effective it's going to be. Even if you look again at this this surface right here, you can see that the surface that we see here, this color here, this shade of gray is much brighter than this shade of gray. And the reason being is close by shades, which would be like, say, C and D, are not affecting this white surface as much as this reflection that's coming from, say, E surface and F surface, which are affecting this corner. And it's basically almost working very similar to how the reflections would work, but this is specifically just a global illumination. All right, so let's talk about gradients. To use gradients, you either go right here to your toolbar, and you can select it from this little drop-down menu once you right-click, and you can see there are a few options to choose from, or by pressing G on your keyboard. Both options will get you here. And gradients are pretty simple. you have 5 different types of gradients: linear, radial, then you have angle, reflected, and diamond. And let's quickly see what they do. There are also gradient modes, which is basically the layering modes that you see right here on your layers menu. Those modes have a different kind of behavior. We'll discuss exactly what those behaviors do and how to use them in your painting on a different time. For now, let's use a normal mode. You can change the opacity. You can make the opacity to be 100%. You can also make it different if you want. Let's use 100% for now. You can make the reverse, which means it will just switch between colors right here. And the color choices that you see right here are basically the colors from your foreground color and the background color. So let's quickly draw something, and the way it works is it's when you click, it's going to create a start point, and as you hold it, you can just